Okay, so the background needed for this course is basically coding. So because you will code here in this course in C, you will code in C++, you will code in MATLAB. So you should have a basic knowledge of these three languages, okay? Also, you should have the basic knowledge of algorithms, analog circuits, because in the second part of the course, in the lab part, you will be interfacing circuits to the robot, the mobile robot that hopefully you guys has taken from the department. I don't know the situation yet. And also the basic of analog circuits like diodes, op amps, and such things. And of course, the basic knowledge of embedded systems. Okay. Okay. So the text box, we have two parts in this course. So the lab part, the lecture part is basically computational motion planning. So you will basically code path planning, you know, graph search and stuff. And for this, we have a text book by Stefan Lavallee, and this is the link for this book. It's a free book. And for the other part, which is the lab part, you should know the basics of, or you should read or be familiar with the name of the processor. The processor on the robot that you will take is called MSB 432. It's a family of processors, but basically they have, you know, some basic functionality. So the book of Ying Bei, the second book in here, microcontroller engineering with MSB 432, is your textbook for or reference for that part. There are also other references. Another book in robot motion planning, the lecture part, as I said, and also the book of Jonathan Valvano. He's a professor at UT, University of Texas at Austin. It's just like the microcontroller one. Okay, it's also about MSB 432. The robot that you will receive from the department is made by Texas Instrument. It's a very good robot, you know, and those guys has made a huge curriculum there in their website. I mean, TI. They made a lot of projects using this robot. So I gave here the link for this curriculum on TI website. You guys go there and, you know, watch videos, read their PDFs. They are making a very good projects, and you will depend on them somehow. Also, the data sheet of the processor of the robot, the technical reference manual of this processor as well, or microcontroller. The microcontroller will be embedded in a launchpad. So the launchpad user's guide is also a reference for us. We will have some information from it. And finally, something called driver library. Library. This will be in the lab. You don't worry about it now. Okay, I will introduce it in the lab section. And finally, the robot itself is called TIRLSLK Max Kit. So it also has a user guide. This user guide will show you how to assemble it, how to interface, you know, how to assemble the motor, how to, all that such stuff. But don't assemble it by yourself, okay? Wait for the lab, because there are some caveats there. If you did some mistake, the robot will be burned out, okay? It will be break. It will break. Okay, so let's go with the classification of robots. There are many classifications for robot, but the one we're interested in is how robots are moving and the environment in which the robot is operating. So you have fixed robots, the one, for example, that paint, you know, cars in industry, or assemble cars, for example. You have flying robots like quadcopters. You have the legged robot or humanoid robot. You have a swimming robot, and you have finally the wheeled robot, which is the most, you know, famous robot, which is, and the most useful. It has many applications. These applications, and this is the ones that we are interested in that course, the wheeled robot. These are some examples of the wheeled robot application. The Mars rovers, they are just wheeled robots. Okay, minesweepers, they look for mines and sometimes deactivate it. Delivery, restocking goods. For example, Walmart now has a project that do that, and lots of other applications of wheeled robot. The study focus and the outcomes is actually in two parts. So we will concentrate our study in two parts. First, which is the lab part, which is the lecture part, the computational path planning. So the basic problem here is that if you have a robot in some environment, how this robot will, discretize or identify the environment around him, and how it will navigate through this environment to its goal. Okay. You will learn, for example, how to build a map for the environment, to follow this map, how to avoid obstacle or risk management, for example, how to get the shortest path between a start and a goal locations, and also a trade-off between graph search algorithms, okay, for such kind of problems. The second part, which is the lab part, you will learn how to interface and how to deal with the hardware of a wheeled robot, okay? And for that, we have the kit that you should receive. And I have a question here. Did you receive the kit or not?
No. What kits are you referring to, Professor?
Nobody has contacted you yet?
No.
Okay, so you guys should receive a kit, a mobile robot, okay? Professor Melissa told me that this should be soon, but I don't know how soon it is. But you should receive it soon. Okay? This soon, maybe one day, maybe 1 week. I don't think it will be more than 1 week, but you should receive it, okay? And we will play with this robot in our labs, okay? Starting from next week, hopefully, if you receive it. And I will contact her today and update you. But anyway, you will receive a wheeled robot kit, okay? And we will play with this wheeled robot kit. We will learn how, of course, assemble it and deassemble it, how the basic sensors of a robot is working, how to interface them to the robot, how the motors of a robot working, what is the tachometers, for example, which measures the speed of a motor, how to communicate with a robot, for example, using UART, and lots of other stuff. Okay, so these are the two parts. The first part is the lecture part. It's basically coding. The second one is, it's a mix of coding, embedded system coding, of course, and interfacing, and it's embedded programming, okay? Okay, this is the kit that you should receive. It's called TI, Texas Instrument, RSLK Max kit. There are two kits of, one is called RLSK, and this is the one that you will take, is called RSLK Max. The first one, it needs some soldering and stuff, but this one is solderless. So everything can just plug and play. It has many features. So first, of course, you have the processor. Let me, annotate here. Okay. Okay. So you have here, for example, the processor. Here is the processor. This is the launch pad, basically, okay, in which the processor is mounted. You have two motors and basically two wheels, of course. Here is a tachometer. This tachometer is just a sensor that measures the speed of a motor, of a motor, of a wheel or a robot. You have here some very good feature, which is it's called bumper switches. So whenever this robot hits a wall or something, those switches will sense that and send some signal to the robot or microcontroller so that we know that this is a wall, for example, we should avoid it. Okay. There is a room here to assemble IR distance sensor. It should be included in the kit that you will receive. This IR distance sensor is infrared distance sensor. So it just sends some signal, the signal reflected back, so the robot can estimate the distance between its location and the wall, for example. Okay, the reflection. What also we have analog low pass filters just embedded in the kit itself. These analog low pass filters, because some sensors have very noisy measurements, so we need to filter this noisy measurement before reading it. Okay. You have what's called line sensors, and we will talk about them in our labs. They are very useful. They are just under the robot. You can't see it here. Okay, they mounted under the robot. Basically, the robot uses this line sensor to estimate its position. Okay, if it's going right, if it's going left, if it's going forward. You have also something called H bridge, which is very useful. So without this H bridge, whatever it is, the motor can go in one direction, either forward or backward. But with this H bridge, you can control the robot to go forward or backward. Okay. What else? Yes, we have also, you know, a bunch of wires and some alligator clips and lots of other stuff. Okay. So this is basically what's included in the kit that you should receive soon. Okay, and let's continue. Yes, what's not included in the kit that you should receive is the batteries. So this kit or this robot are operated by batteries, actually 6 AA batteries. So you need to buy these batteries. Okay. So you have the best option, go to just Dollar Tree and buy, there is a bag there that has 6 AA batteries with $1, just $1. Or you can, you know, if you are rich, you can buy this rechargeable energizer batteries, which is very nice, just $14 on Amazon. Okay. And by the way, this is the recommended batteries for this robot, because the motors consume a lot of current. Okay, so if you just use normal batteries, you will change them a lot. Also not included in the kit what's called ultrasound distance sensor. So if you remember in the last slide, I talked about I talked about IR distance sensor. That's what's included in the kit that you will receive. This sensor, as I said, uses infrared signals to estimate distance between the robot and a wall in front of it, for example. But there are also other types of distance sensors. Let me go. Yes, clear room. Yes, which is ultrasound distance sensors. Okay, these ultrasound distance sensors is just like the eye infrared sensors, but use ultrasound, not infrared signals. Okay, and they are cheaper than the IR sensors. For example, you can get 5 of them with a couple of good wires, good wiring for them, interfacing wires, with just $10. If you just buy one, I think on Amazon it's just $5-something. So it's good to buy those sensors. It's optional. I bought them for myself, but if you guys, if you all guys bought these 5 sensors, we can implement a lab using them. If you all bought it, okay? But you must buy the batteries, of course. Also, it's not included, but it's very encouraged to buy. It's just multimeter, just $10 on Amazon, because you need to debug the circuit that you have, the robot, I mean. You need to know if the batteries are low, and you wouldn't know that just by, you don't know that unless you have a multimeter to test the voltage and the current. Okay, so the multimeter, this cheap multimeter, is very enough, and it's good if you have one. Because of course we don't have an actual lab, everything will be virtual. So you must have some basic stuff in your home, you know, to test and debug the circuits that you have. If you are a millionaire, you can buy, you know, this pocket oscilloscope. It's very nice. It's very small, just like, yeah, this size, I think. I got one. It's around $100 on Amazon, but it's very useful. And it's actually double channel, so you can see two signals at the same time. And also it has a generator. You know, most oscilloscopes, or maybe all of them, has an internal signal to calibrate the oscilloscope. And this guy, which is very small, has this kind of feature. If you are a billionaire now, you can also buy a thermal camera. Okay, all of course this is optional stuff. Okay, but why a thermal camera? You remember I said that we have the IR distance sensor. Okay, it emits infrared signal, which is not seen by our eyes. So if you want to know if this guy is working or not, you cannot sense or cannot see the infrared signal. If it's normal LED, you can see the light. But this guy is infrared LED. So to know if it's working or not, we need something to see the infrared signal, which is of course a thermal camera. Okay, thermal camera or thermal lenses is the only way by which you can see an infrared signal. It will be of course like red because it's hotter than the surrounding. Okay, but these are optional stuff just for debugging. Okay. Yes, let's go. So computational path planning, this is, as I said, our basic field of study in the lectures. And in this problem, you have 4 inputs. You have the environment geometry of the robot. You have also, let's annotate here. Good. You have the environment geometry of the robot, the surroundings. You have the robot geometry itself, because the robot is not considered as a point. Okay, the robot has a certain size, certain shape. So there may be a gap between 2 obstacles, but this gap, for example, is very small or very tiny to the robot size. So the robot cannot go in these small gaps. So the robot geometry or shape should be taken into consideration when we construct a path between a start and a goal location. If you didn't understand this or didn't imagine it well, just don't worry, we will come to it in the next lecture. But just for now, the environment geometry is important, the robot geometry is important. And of course, the starting position and the end position. Based on these 4 inputs, the path planning algorithm will determine for us a path between the start to the goal. Okay. Yeah, should cancel every time. Okay. There are basically 3 techniques for the path planning. The first one is called discrete planning. Okay. So the robot is not a human. It needs some way to identify the environment around it. So this environment usually has obstacles. So there are regions with obstacles, which is forbidden for the robot. Of course, it will hit them. And there are free regions. And the robot needs to identify the free regions and the forbidden regions or the obstacles. Okay. One way to do that is using this discrete planning. For example, this is one of the examples of discrete planning in which these are the obstacles. So these guys here, let's make them black, are obstacles. Okay, Good. And these obstacles, you know, has vertices. Those vertices, let me, yeah, those vertices. And also this guy. So from each one of these, this is one of the ways of discrete planning, is to make or draw a line from each one of these vertices to the, until it hit an obstacle or it hits the wall. So for example, for these vertices here, we draw a line, we stop here because we hit a wall, we stop here because we hit a wall. For this one, we draw a line, we stop here because we hit a wall, we stop here because we hit an obstacle, the same obstacle, of course. This guy, this vertices here, we draw a line until here because it hits an obstacle, then to here because it hits the wall, and so on. So let's clear all just, yes. Until we have those areas here, okay? So we have here one area, for example, let me draw this, yes, yes. We have here one area, this area. Which is free. The robot can move freely in this area. So we assign this area as a point in our plan, this point. This point in here. This is the first point in a graph. We have also another area. Let's draw it or highlight it with another color. This area here. Okay, and again, the robot can move in this area freely. So we can assign a point in our graph for this area. So this point represents this area here. Then we can connect these points together or connect these two areas together. So for the robot now to move from this area to this area, it should follow this path here. Okay? Of course, you will say to me, do we care about the location of this point or this point? Should it be, for example, here? Can it be here, for example? Or can this be here, for example? This is just a details because, of course, when you construct or you choose this point, you should avoid, when you draw a line between them, you should avoid hitting an obstacle. So this is just an overview about the discrete planning. It's not a separate lesson, just overviewing the idea. And we will do the same for other areas as well. So we have also here another area, this area here, okay? We have another area, this area here. And for each area, there is a point, okay? Until we construct a graph. This graph that you can see here. This graph is your map for this entire environment. So this is your environment now, okay? And the robot is sure that if he moves on any of these edges, it will not hit the wall, any of the obstacles or of course the wall, of course, in the environment. Now, based on this map, if the robot, for example, the starting position of the robot was here, then we can connect this starting point to the nearest edge in the graph. And if the goal, for example, was here, we can connect this to the nearest edge on the graph, and then we can construct a path between them. Okay, very simple example, but gives you a good idea about what we are doing in path planning. Okay, don't worry about the details. Where should these points located? Should we choose, for example, this point to be here or here? This is the details, okay? I'm just giving you the overall idea, okay? Any questions? Should we proceed? Don't be shy. Let's proceed. Okay. Yes. Another idea for discrete planning, we're still in the first type of path planning, which is discrete planning. Another idea to come up with a map for the environment is using the simple, what's called simple decomposition, this guy in here. So let's annotate again here. Okay, using another color. green, for example. Simple decomposition. This is very simple, as the name suggests. Just discretize the map or the environment of the robot as a mesh. Just squares like this, okay? And if any of these squares are intersected with, so this is the obstacle in here. This red thing is the obstacle. So in our map now, if any of these grid cells, those grid cells, is intersecting with our obstacle, so this is a forbidden cell, and the robot should avoid it. Okay. So if we let's change here the color, make it, for example, yes, brown, for example. So since this cell, although it has some free area here intersecting with the obstacle, I will consider it all as forbidden. This cell, again, although it has some free space, but since there is a tiny portion intersecting with the obstacle, I will consider it as a forbidden. I cannot use it in my path planning. Again, this one. Again, this one. And this one. This one. Or these two. These two. These four. These four. These three. And finally, these four as well. It's clear in here is that if we make the grid cells tiny, then we are avoiding wasting, some cells, because this cell, for example, it's just a tiny portion that was intersecting with the obstacle. So if we make, for example, the grid size like this, then we will make this as filled, but this portion here will be free. I'm sorry, it's just this portion here will be free if we make the grid cells finer than this. Okay, what is the problem with this simple decomposition? Although it's very good and very easy, you have 96 cells, and you may have hundreds of thousands of cells if the environment is very large, or if you have a fine grid than this. Okay, as long as you make the grid finer, you will use more computational memory, or more memory storage. So we came up with a different idea. So this is the simple decomposition. There are a more clever idea. Let's see it, which is iterative decomposition. In here, we start with bigger or coarse grain size. Of course, here, the square here is much bigger than, it's actually equal to 4 squares in this one. So less memory usage. Then we do what we did before. If any cell is intersecting with the obstacle, it will be a forbidden cell. So let's do that. Let's see what's forbidden and what's allowed. This cell in here will be forbidden. So all the cell, I'm sorry, let's choose another color. Yes. This cell will be forbidden. This cell will be forbidden. This one also. This one also. This one. This one. This one. These two. And finally, these two. Then we try to find a path between the start and the goal based on that meshing or size of mesh. Clearly, we cannot find a path between the start and the goal. So we decided that this grain size or the cell size was very big. So let's decompose it. But the clever thing here is that we will not decompose all the cells. We will only decompose the cells that are mixed. I mean, for example, let's clear what's, yeah. For example, this cell here can be considered completely free. There is no intersection with the obstacle. This is also completely free. This is completely busy or whatever, occupied, name it whatever. But this one is mixed. Some part of the cell is free. A tiny part here is intersecting with the obstacle. So these are the cells that will be decomposed. We will not decompose all the cells. So if we do that, let's do that here. Yes, I did it already in the Excel. Yes. So if we do that, if we just decompose this cell and this cell and this cell, this cell, this cell, this one, and this one, and this one. Now, based on that, those two cells in here are free. And if we run the graph search, we can find the path between the source, our source in here, and our destination or goal. How many cells in here? In this simple decomposition, 96. How many here? Only 85, almost half, or maybe 40%. Okay, which is still good, very good. So we save 40% of the memory used by this simple decomposition. Okay, so those are examples of how of the kind of problems that you will face in this you know in this course. Let's move on. Any questions? Again, don't be shy. Any questions?
Nope.
Okay, so let's go forward. Yes. The second, so this was the first type, which is discrete planning. The second one is called sample-based planning. So as we see with the discrete planning, we use a lot of memory, right? And maybe for some problems, we don't need such, you know, maybe the obstacle is small, for example. So we don't need to discretize all the environment. So they came up with another method called sample-based planning, in which we just choose random points in the environment and check if this point is intersecting with an obstacle, then we avoid it. If it's away from the obstacle, then we include it and connect it to our graph. Okay, so let's, for example, say here, annotate here, using, for example, okay, yellow, that's fine. So in the beginning, assume that we have only the start point and the goal point. Okay, then we'll generate some random number. I'm sorry, not random number, two random numbers. One for X and one, this is X, and one for Y. This is the coordinates of the point that should be a candidate to be included in our graph. And this graph will represent our environment. Okay, let's assume that, okay, this is the point that we generated. Is this point included in the obstacle? No, it's a good point, it's included. We have a point. Generate another point, for example, this one. Okay, is this point included, intersecting with the obstacle? No. Can we draw a line between this point and the previous? Yes, we can draw a line. So yes, we have our first edge in our graph. Okay, and doing the same for the other points. Generate the point, check if it's in the intersecting with the obstacle, and if you can connect it with the graph or not. Okay, until, for example, some some number of iterations. Okay, I'm sorry here. Just yes. Until you exceed some number of iterations that you that you run the algorithm to, or for example, you know, you reach it very close to your destination or goal, anything like this. Okay, you can put your criteria for ending the search or building the graph for your environment. What is good about this is that you represent your environment with less point or less meshes, with less number of grid size, we can say, than the other the discretization method. Okay, this is another method that you know we'll see in the future in this course. It's a very nice one. Okay, so let's go forward. Oh, we need to. Yes. Okay. So another, it's yes. The third kind or third type or technique of path planning is called probabilistic path planning. Okay. And here now, when you build, for example, a graph like the one that we just see in the previous slide here. Yes. For this graph, for example, if you want to know the path between the source and the destination, okay, you just run very, you know, very simple graph search, you know, graph algorithm. Then you can, for example, you know, determine that this is, for example, the shortest path between the source and the goal, and that's it. Okay. And your criteria here is that this is the graph, for example, that you know the robot, if it follows this path, it will you know move for shorter distance, so it will reach its goal in shorter time. Okay, but for probabilistic path planning, it's different here. You will consider other factors in determining the path between a source and a goal. One of these factors is the risk, for example. So the source here, let's draw that. The source here is here, and this is the goal. What is the shortest path? It should be, if all, you know, if all the distances are the same, it should be something like this. But for this path in here, we will pass through a lake. So there is a risk that the robot maybe, you know, fall down this lake or something, and we just lost it. And these robots usually, for example, very expensive. Even if it was cheap, don't play with this. Another short path that can be considered shortest path is this way. This is 2 hops. I'm sorry, 3 hops. 1, 2, 3. And this is also 3 hops. 1, 2, 3. But what is the problem with this second path is that you will pass through a cliff, like a mountain or something. So there is also a probability that you may lose your robot. So if you consider this in probabilistic path planning, we consider these kind of factors and build, you know, a probabilistic model. Something that says if the robot is here, 10% takes this direction and 90% takes this direction. Then you generate, for example, a random variable between 1 and 100. If this random variable is between 1 and 90, take this path. If it's between 90 and 100, take this path. So it's a probabilistic. Okay? So using this probabilistic path planning, the shortest path now, because you have another criteria to consider the shortest path, will not be this guy, will not be this guy, it will be this new guy here. Okay? Because this is the path with the least risk. Okay? So this is a third technique for path planning. Okay. Now, how to evaluate a path planning technique? There are 6 criteria that we can, compare a technique to another technique. First, completeness. So if you have a graph search algorithm, for example, we can consider this graph search algorithm is complete if it always find a path between the source and the goal, if of course there is a one. Because for some problems, there is a wall, for example, that you can't cross. So an algorithm is complete if it can all the time find a path between a source and a goal, if one exists. And it will return, for example, like not valid for something like this if it doesn't find. So if it says that I can't find the path, we are sure that this guy is saying the truth and there is no path between the source and destination. This is what's meant by a complete algorithm. The second criteria is optimality, which is judging the path that the algorithm returns for you. So this path is the algorithm returns, for example, move right, then move left, this move forward. So if that path is the shortest path, okay, so this is the optimal path. Okay. 3, the speed of computation. So you may have an optimal, complete search algorithm, but it's very slow. So another factor that we take into consideration is the speed of computation. Also the memory. So for a graph algorithm to make some decision, right, sometimes it needs to look at the history, for example, make some computation, look at some data. So this data consumes some memory. So how much memory it needs to give you a good decision. Number 5 is risk avoidance. Like what we said, an algorithm may give you a shortest path, but this path is not secure. This path maybe is passing through a lake or a cliff or whatever, danger. And finally, the generality. So a method can be used in many applications, okay? Maybe not optimal or maybe not complete, but it may be very simple to be used by many applications. But another algorithm may be optimal, it may be complete, but it just valid for 1 or 2 applications. Okay, so these are the 6 factors that we evaluate a pathing technique using. Okay. Basically, there are, we will study first the discrete path planning, okay? And the discrete path planning needs 3 steps. First, constructing what's called the configuration space, okay? In simple terms, this configuration space is what you are seeing in here, okay? In which there is a grid for the environment, some sort of discretization, and some grids are valid to pass, like this one, for example. The robot can move through this cell, and some of them are not valid for passing, like this one, for example. Okay, but the configuration space is also taken into consideration, not just the obstacle in the environment, but also the dimension of the robot. Okay, don't worry about this definition, we'll come to it later. Okay, but to construct such a grid, we need 2 things. We need the environment geometry. For example, here is where is the obstacle, and we need also the robot geometry. Okay, I just explained how we construct this grid, assuming that the robot is just a tiny point in the grid, but we should also consider the shape of the robot. Okay. The third step, which we will start with because this is the easiest one and the more convenient for you for understanding, is the graph search. So after constructing such map, okay, knowing what's free cells, what's occupied cells or forbidden cells, how can we construct a path between a source and destination? Okay, let's clear all of that. So now let's go to graph search algorithm, the third step. So we'll skip the first one and second one. They are just a little harder than the third one. So we'll start with this, and don't worry, okay, everything will be fine, and we'll go back later to the first two steps. So graph search algorithms, we will talk a bunch of them. Maybe we will take 6 graph searches, so in 6 lectures. So basically, there are 2 types of graph search algorithm: uninformed and informed. Okay, what's uninformed? Uninformed graph search algorithm is an algorithm that take decisions in the search without considering the goal location. So whatever the goal location is, the same steps will be taken each time. So for example, if it tries to start searching forward before right or left, it will do that whatever the location of the goal is. Maybe the location of the goal is backward, so it's better to go backward or search backward. You will reach faster, or you will find the goal faster if you look backward before forward. Okay, so an uninformed graph search algorithm is the algorithm that searches in certain pattern, regardless of the goal location. Also, informed search algorithm, okay, take into consideration the location of the goal. So if the goal is backward, okay, I will do some calculations, then I will start backward, then searching forward. Or if the goal is on my right, I will go in the right direction or search in the right direction first before going or searching in the forward or backward or left direction. An example for the unformed algorithms, we have many examples. We have, for example, the breadth first search, depth first search, and many others. And the most famous informed algorithm is called A star. We will talk all of these guys. Okay. Okay. So yes. Let's start by breadth first search, BFS for short. Okay. What's breadth first search do? It just go widely before depths. I don't know how to express it, but if you have many directions, if you have 4 directions to explore, for example, if I am a robot and I have 4 directions to go to, I can go forward, I can go backward, I can go right, and I can go left. So I will explore all of them, okay, at the same time. So in each step, I explore one possibility in each direction. So for example, search here for 1 minute, 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 okay, in all directions. Then I go bigger, okay, the circle will be enlarged, okay. It will be more clear if I explain on the graph that we are seeing right now in front of us here, okay, just yeah. Okay. So how to explore, for example, this graph that we are seeing right now? If this is the start node here, okay, I will consider it.
Dr. Abdulharim?
Yes.
A quick question. So when you format the code for this robot, is it basically creating like a binary search tree? Because this looks similar to a binary search tree.
Yes, yes, yes. So basically the robot using algorithms, searching algorithms that you used before maybe, in some other courses to construct a path to its location.
Got it. Thank you.
One of them is binary trees. So you remember the sample-based algorithms? So one of the sample-based algorithms is constructing a tree. Okay, it's called a random. It's called RRT. I can't remember what is this abbreviation is for, but it do something like this. Okay. So let's see how Brett's first search will do in here. So if this is our starting location, I need to keep the annotation. So yeah. Okay. So if this is, for example, number 1, so I have here 2 options. This guy, number 2, and this guy. Oh, I'm sorry, I just forget something in here. Yes, yes, yes. And this guy will be, oh, I need to make his annotation again. Okay, and this guy number 3. So we have 2 possibilities. Number 1, if I'm starting from here, okay, I have 2 possibilities, this guy and this guy. Then we go 1 step forward, assuming always that left is before right. Left before right. You can do the opposite. You can do right before left. So we have 2 possibilities, 2 and 3. I will start by the left, which is 2. Okay, so 2 has 2 other options, 3 and 4. Then, just to make a uniform search, we go to the other option, which I started from 1. So we have here 5, 6. So this is the order of the search I'm going for. 1, 2, 3. I'm sorry, 1, yeah, 4. I'm sorry, this is 4. Oh. I'm sorry. Okay. This is 4. This is 5. Then I explore the possibilities with 3, which is 6 and 7. Okay. Then I go to 4. And we have here number 8, number 9. This number is can be considered the step at which I explored this or reached this, this location or this cell, for example. Then 5 here, 2 possibilities, 10, 11. Then number 6, 12, 7 here we have 13, 14, and so on and so forth. So I'm going equally in all directions. I'm not favoring one direction over the other. Okay? So let's see here the solution for this. Yes. Yeah. So look, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 8, 8, 9, 10, 11, 12, 13. Yes, we are right. So guys, I will give you 2 minutes just to continue on my in the same way and give me an answer for what should be the step number of A. Where is A? Well, yes, A, B, and C. I'll give you 2 minutes just to give me the step number of A, B, and C. Let's start now.
Professor, B and C are cut off for me. It cuts off right underneath A.
You can't see them?
I can only see A. After that, the rest of the tree is cut off.
Oops, that's a problem. Okay, let me.
It's good for me.
It should be okay with you. Chris, with me?
Yeah, but let me see if I can change maybe a setting or something.
Is it because you're mute and like participating chat is covering it? Is that what you're trying to say? Because if you move your mouse away from the screen, then that bar disappears and it shows.
Yes. Yes.
Let me try that. Oh, there we go.
Good.
Thanks.
Good. So you guys, you have 2 minutes. Okay, any solution? Anyone?
For A, I got 31, and then
Okay.
B 32, and C 36.
Oh, let's check this. So 18, just go 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, right? 32, right? 33, 34, 35, and 36. That's right. Of course, if this is a real problem, okay, you will stop at the goal. So for example, if this is the goal node, for example, you will stop here. You will not continue. Okay, so you will not explore these, these nodes. You will just stop here. Okay, and this is what we will do in our next, It's just check first. Oh, it's not here. That's fine. In our next slide here. So we'll just remove all these annotations, which is annoying. Yes. And okay. So let's do this now, this example now in more algorithmic way. So to do the breadth first search, we need basically first in, first out FIFO, or I don't know, memory, or Q. You guys are familiar with first in, first out FIFO or Q? Anyone is not familiar?
Yeah.
Good.
Where was it?
Okay. So to do that in a more algorithmic way, we need a FIFO or FIFO, whatever you call it, okay, which is first in, first out queue, priority queue. So let's have a convention here, which is going up, then right, then left, then down. Whatever goes, the order, it doesn't matter, okay? So this is a start node, this is the goal node. And let's now explore the map until we reach our goal cell. So, okay, this is the queue in here. And we will start with, we will put our first node here, which is S. And since it is the only one in the queue, so it's the first in and also the first out. So we'll explore S. And we will go up, then this is 1, right, 2, left, 3, down. You can do your order, that doesn't matter, okay? So we will put in the queue here 1, 2, 3, 4, okay? We finish this, start, then remove it from the queue. It's explored. Don't return to it again, okay? Then, first in, first out, which is 1. So we'll start by 1, explore 1. So 5, 6, 7, and this is explored, don't count it again. And add those new nodes, 5, 6, 7. No other options for 1, remove it from the queue. Then 2. 2, we have here filled, explored, then right, so we have 8. Just take the one number larger than this guy. It's the last one in the queue. 8, explored, then 9. So add here 8 and 9. Remove 2. Then we go to 3. This is 3. Explored, a wall. This is guys a wall. So the robot should avoid. We have only one option, which is this cell, which should be 10. So this is 10. Remove 3. Then we go to 4. This is 4. All are occupied. This is 11. 11, remove 4. Then we go to 5. 5 has 3 options. So 12, 13, 14. 12, 13, 14. Remove 5. 6. 6 have one option here, which is 15. Remove 6. 7, all are explored. Remove 7. 8, where is 8? Just one here, one option here, so 16. 16, remove 8. 9, only one option. 17, 17, remove 9. Then 10, one option. 18, 18, remove 10. Then 11, no options, remove 11. 12, 3 options, so 19, 20, 21. 19, 20, 21, remove 12. Now 13, one option, 22, remove 13. 14, where is 14? Yes, no options, remove 14. 15, 15, where is 15, guys? It's no options. 16, one option, so this is should be 23, just one, add one to this guy. Then 23. Then 17, where is 17? One option. 24, remove 17. Then 18, where is 18? No options, remove 18. 19, yes, 19 here, we start with up, so this is 25 and just stop. Why? Because this is the goal. Okay, we reached the goal. Okay, so we explore all these cells to know where is the goal is. Okay, so this is what's, so it's like a circle that goes like this, that enlarge in its radius until it reaches the goal at some moment. Okay, this is breadth first search. We go wider all the time in all directions. Okay, so we took here 25 steps to reach our goal. Okay, so let's clear all drawing. Undo. Why undo? Because let's check if you are correct or wrong or not correct. So I have here the solution. Yes, we are correct. Look at the two numbers, 19, 19, 21, 21, 12, 12, 25, 25. So we are correct and our method actually works. So let's remove all such, garbage. Okay, so we took 25 steps to reach our goal with the breadth first search. Now, how to construct the shortest path, okay? This is actually a very easy way. So each cell, as we see here, has an index. That index tells you at what time, or what step this cell was explored. There is another index, or a number associated to each cell as well, which is its distance from the start. Okay, so, and by this step here, we will determine the shortest path between. So after exploring, so this is the first step in the first search. The second step is to determine the shortest path with this method that I will just mention right now. So first, what is the cells that are one cell away from the start? This cell is one cell away, this cell is one cell away, this cell is one cell away, this cell is one cell away. Okay? Okay. Now, where are the cells that are 2 cells away? Those cells should be the cells that are 1 cell away from the cell that is 1 cell away. So where are the cells that are 1 cell away? Those are the cells that are 1 cell away. So it should be 2 cells away from the start. This should be 2 cells away from the start. This should be 2 cells away from the start. 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 Now, where are the cells that are 3 steps or 3, not 3 steps, 3 cells away from the start? These cells should be the cells that are adjacent to 2. These cells in here. So this is 3. Yes, it's 3 cells away. 3, 3, 3, 3, 3, 3. Now, where are the cells that are 4 cells away from the start? Those are the adjacent cells to the 3s. So 4, 4, 4, 4, 4, 4. Let's check, for example, here this is 1 cell, 2 cells, 3 cells, 4 cells. Okay? So now, where is the cells that are 5 cells away from the start? If we start by this one here, this is 5 in here. And this is our goal, so we just stop. And now, where is the shortest path? Just go to the cell that is 1, that is just to -1. So this is 5, go to the -1, which is 4. So we'll go from here to here. Let's change the color. Yeah. Okay, so go from here to here. From here, just to go to the cell with just 1 minus. So it's 4 minus 1 is 3. So go here. Go 1 minus to here. Go 1 minus to here. Go 1 minus to here. So this is, can be considered as 0. So this is actually the shortest path between the source and the goal. So we did 25%, I'm sorry, 25 steps in breadth first search, although our goal is just 5 steps away from our start or starting point. Okay, so we just ran out of time for today's lecture. So next lecture we will start by another algorithm called the depth first search. Then we will start coding. So to prepare yourself next time that we will code together. Okay, and as I said, this coding that you will do each lecture will be counted as, you can consider it as a part of assignment. Okay. So guys, any questions? Any questions?
Are we going to have access to these slides or?
Yes, I will send them to you. Don't worry. I will send them to you. And also I will publish this recording to my YouTube channel and send you the link as well. Okay.
Will you send it through email or through Canvas?
Canvas.
Okay, thank you.
Okay. So guys, if you have any question, just if you don't have now and you study this lesson and you find some question, just ask me before I start next lecture. Okay. Say, Dr. Mustafa, I have some question from the last one. And just, you know, if you wanna email me anytime, and you also have the Zoom hours, okay, which is Thursday. Okay, guys, have a nice day.
Professor?
Okay, thank you very much.
Professor?
Yes.
You'll update us if they send out the robot kit, right?
Yes, I will send it to Dr. Melissa today, because she told me 2 weeks or 3 weeks ago that they are processing the, you know, the delivery of the kits to you.
Okay.
But there are some procedures, you know, for the safety of you, you know, some forms to fill and, you know, some paperwork to do in order for you to take the kit. But I really don't know what is the status of this. I thought that you already got it.
Oh yeah, we didn't get it. Yeah.
That's fine. So I will email Professor Melissa and get back to you.
Okay. Sounds good.
Thank you very much and have a nice day, guys. Okay. Bye-bye.
Thank you.
Bye.